Hello, in this video we're going to be discussing some interesting applications to particle-in-a-box theory and some stuff that's just downright weird. We'll start by talking about the basic theory behind what's called quantum mechanical tunneling, which is going to lead to some very non-classical behavior in atomic and molecular systems, and it's just, as I said, just downright weird stuff. It can give you headaches if you think too much about it. And then we're going to look at some applications of this tunneling to imaging of atomic and molecular systems involving something called STM, which is scanning tunneling microscopy, and AFM, which is atomic force microscopy. So let's just take a look then at some of the basics here. What we're going to do is we're going to take our particle-in-a-box system where we had a potential energy that was infinite outside the box, and we're going to make that potential energy, instead of being infinite, be a finite, meaning that it has a value which is not infinite, which will have a major impact on the results of that particle-in-a-box system. Inside the box will maintain the same behavior, the same potential energy, which was equal to 0. So the only difference here in this new model is the potential energy outside the box is not infinite. So how does that affect things? Well, we end up again with two equations associated with whether the particle is inside or outside the box. Of course, inside the box, where the potential energy is 0, we actually have the same equation as we did before, where we just have this first term, which is the kinetic energy term. Outside the box, however, the difference is that we actually have a non-infinite term that plays a role in the solution. Now, in this particular system, we're actually not going to go through the mathematical derivations associated with these equations. We're just really going to take a look at the results and what it all means. The first thing we're going to note with regard to meaning is that because the potential energy is not infinite outside the box, that the wave function outside the box is not equal to 0, meaning that there will be some probability that we can find the particle outside the box. Since the wave function is not 0, the probability density will not be equal to 0. So let's take a look at this. So here we have just a diagram which shows precisely what I was saying, that we have this region outside the box, which is indicated here in yellow, as being the region where we have a finite potential, again indicated by this V naught right here. And of course inside the box, between, in this case, negative A over 2 and A over 2. Notice the length of the box is still equal to A, as it was in our first model, but it turns out for convenience purposes in the solutions of the equation, it's just easier to go from minus A over 2 to A over 2. Those are just arbitrary limits. The length is the same, but the solution is easier if we do it this way. So we also see that in this particular case we end up with energy levels indicated here again by n equal 1, n equal 2, etc. And wave functions. Now the deal, of course, is the wave functions do look very, very similar to the ones for the infinite potential case. The only difference is, of course, they fall off, and you'll notice there are regions where the wave functions are non-zero outside the box. So we can see this here for n equal 1. There's a region where outside the box you can see the wave function is not 0, and on both sides of the box, and the same thing for n equal 2, etc. So we do have these regions outside the box where there is a non-zero probability. Now, one thing that's important to note here, and this is where things should start blowing your mind a little bit, and that is that the dashed lines here represent the total energy of the system, and in this region outside the box, for example, at n equal 1, right here, we will see that the total energy is less than the potential energy. Well, remembering, of course, that total energy is equal to kinetic energy plus potential energy, if we have a situation where the total energy is less than the potential energy, what does that imply about the kinetic energy? Well, what that implies about the kinetic energy is that it must be negative. So this is a very, very non-classical situation. We just do not see kinetic energy is less than zero. The reality is that when we start doing observations of systems like this, we will not observe a particle in a negative kinetic energy state. When we make the observations, it will always be in a positive kinetic energy state, but it does lead to some other weird results that we're going to talk about in a few minutes. So let's go ahead and talk about that, and let's say we have a wall with potential energy V0 that's a finite width. So we have essentially a system that, and the diagram's on the next slide, but I'm going to go ahead and draw it here just to make this clear what I'm talking about. So it's like we have, here's our wall on both sides. So we have V equals 0 inside the two walls, and then V0 is the height of the wall, and then V equals 0 outside the two walls. All right. So this is what we're talking about. When we solve the Schrödinger equation, equations for this system, and apply boundary conditions, we find that the wave function will decay from inside the box exponentially through the wall itself. So in other words, we're going to notice that our wave function might decay like that. That would be an exponential decay through the walls. And the appropriate equation for this exponential fall off through the walls is indicated by this exponential function here, where the kappa in the exponential term, you'll notice, depends on the mass of the particle and the difference between the total energy and the potential energy inside the wall. So what this means is that that the fall off is greater, okay, if the mass is greater and the difference between the potential energy and the total energy is greater. So the larger the difference, the larger the mass, and the larger the difference between the potential energy in the wall and the total energy, the faster it falls off. And if it falls off faster, then that means there's a lower probability for finding the particle outside the wall. Okay. So let's take a closer look at this. Here we have a diagram that shows the wall finite width, and you see here's our wave function for two different states inside the box. Okay, one state, the lower energy state, where the total energy is 1/4 of the wall height, the potential energy, and the other where it's 3/4. And we get inside the wall this exponential decay that we talked about, right, in both cases. But again, as we noted before, you'll note that as the energy gets closer to the potential energy, the fall off is slower. So when the energy is 3/4 up here, 3/4 V0, it falls off more slowly than when it's 1/4 V0, as we see here. So what about outside the box? Well, you know, outside the box, if the wave function is non-zero, that means the probability of finding the particle outside is going to be non-zero, and we certainly see that it's non-zero here outside the box. And what that means is that we can start with a particle inside the box with this wave function here, but then if we make a measurement, there is a finite probability that it would be out. We might find it outside the box, even though the energy is insufficient to surmount that barrier. Okay. Again, you can think of this in a situation where you have, say, a particle or a ball or something rolling around in a valley of some type, some kind of well, and it doesn't have sufficient energy to get over a barrier, so it might be rolling back and forth classically between these two positions, but the kinetic energy is not such that it can make its way all the way up the barrier and over to the other side. And this is a situation that we would expect classically if the total energy is less than potential energy. It can't get over the barrier. But what we're saying is that somehow, even if the total energy is less than the potential energy, there's a finite probability that we might find it beyond this barrier. All right? Again, we'll never find it inside the barrier, and we can't say, remember we talked about this earlier, we can't say anything about particle trajectory in the absence of observation. All we can say is that the particle started out inside, and then we make a measurement, and then we find it outside. It's like it just appears outside the box. It's like, boom. You know, it was inside the box, now it's outside the box. We can't say anything about how it gets from one place to the other, even though the energy is not sufficient to surmount the barrier classically. This is called tunneling. It's a quantum mechanical effect, and if you think about it a lot, it's very, very weird. And again, you know, as we noted, the difference between the 3/4 V0 and the 1/4 V0, if we look at the region outside the box, there's a much greater probability of finding it for the 3/4 V0, and this is what we said earlier. The closer the total energy is to the potential energy, the more likely we're going to be able to see this tunneling effect. Okay, well that's all well and good, but really, does this actually happen? It's bizarre. Well, there are many chemical systems for which tunneling has been observed. This is a case here which shows a reaction where we start with this molecule which has, you'll see, a four-membered ring in this process, and its energy is insufficient to surmount a barrier, and this two form a five-membered ring. Okay, you can see that there's a five-membered ring, so it involves some bond breaking and bond forming to go from a four-membered ring to a five-membered ring. And here we'll see that there's the situation where we got a bond formed right here that opens up the ring. This bond breaks, this bond forms, opens the ring to get the five-member ring. And again, this is something that there is a barrier that has to be surmounted classically to get from the four-membered ring to the five-membered ring. But quantum mechanically, we'll note that it's been observed that the rate for this reaction is much faster than would be anticipated if the molecule had to surmount that barrier. It's orders of magnitude faster. And so this is a situation where we had this tunneling effect, that even though the total energy is less than the energy necessary to surmount the barrier, we'll still get the reaction occurring at a very rapid rate, and that is an example of quantum mechanical tunneling. We also know that this kind of thing happens. It's been linked to, for example, DNA mutations where hydrogens may tunnel from one part of a DNA molecule to another part of a DNA molecule to generate a mutation, and all kinds of other interesting effects. The recombination of H plus protons and hydroxide ions in solution occurs much more rapidly than should be the case if we just had simple kinetics where the ions were moving toward each other. It's a much faster reaction, and that's an indication that tunneling is going on there, where the proton starts in one point within a solution and then all of a sudden at another point in the solution, and we get a recombination that occurs as a result of that. So these are real effects, and it's very bizarre. Again, remember, we can't say anything about trajectory. We cannot say anything about trajectory. We can only say that it was here and now it's here. Alright, so let's look at some of the imaging effects. The scanning tunneling microscopy is an effect where electrons tunnel between a probe tip here and the surface of something that the system is exploring. So there's an electrical current that occurs as a result of electron tunneling. The scanning tunneling microscopy system actually will monitor the current as the probe passes over the surface. And what happens is that typically these systems will, the current depends on the distance of the tip to the surface. As the distance increases, the tunneling current will in fact decrease, and so that's actually monitored by the electronics. In reality, what's going on here is that the systems are set up so that the current is maintained at a constant value, so the tip is actually moved up and down in order to, as it passes over, and from atomic level, this is a very bumpy surface here. So as the tip passes over it, it moves up and down to maintain a constant current, and that moving up and down is monitored to generate an image on a computer of the surface of whatever is being examined. Scanning tunneling microscopy is, as I said, is used to generate images of the surface of materials. It does require that the materials be conductive because electrons are tunneling between the probe and the surface of that material. But as a result of it passing, we can generate images, as we'll see in a few minutes. The other one that we're talking about is atomic force microscopy, which is not really a tunneling effect, but it's another method that's used to do imaging. In this case, the difference is in atomic force microscopy, a conductive surface is not required. We have a tip and it passes over the surface, and that tip is on kind of a cantilever setup so that the interaction with the surface, as is the case for scanning tunneling microscopy, there's an interaction with the surface which is based on van der Waals interactions, and repulsive interactions causes the cantilever to move up and down on the surface, and there's a laser beam then that's reflected off of the cantilever, and as the cantilever moves up and down, the position of the laser beam on the photodetector moves up and down, so you get this situation again where the surface is actually adjusted to maintain a constant distance, and it generates an image. Okay, and again in this case, here we have the tip. Here's the probe tip, and here are the atoms on the surface. Again, we don't require conductive materials because basically we have repulsion between the tip and the atoms in the surface, and as the tip passes over the surface, that repulsion causes the tip to move up and down, as we mentioned before, and that's how we generate an image of the surface. And as we mentioned before, we're talking about van der Waals interactions here. Here are some images that we see that show the results of some of these scanning methods. The image here at the top is actually just a model that's generated by a computer program. But here we have the STM image, which is kind of blurry, but you can kind of make out some of the features of the molecule. The atomic force microscopy on these systems generates a very, very nice image of the pentacene molecule. You can see the quote-unquote bonds, which are just based on, of course, electron density. And again, this is all based on van der Waals interactions, but we actually get a very nice image of these molecules. And here are, this D here shows several of these molecules that are on the surface of the material as the AFM is scanning over it. Alright, here are some other images where we can clearly see the different molecules. Again, we have some STM images, and then we have the atomic force microscopy images, which show the image of this particular molecule, hydroxyquinoline, as shown here, and you can really see the structure of this through the atomic force microscopy results. And here's one. This is really quite fascinating because you actually, in this case, we have clusters of molecules which actually show hydrogen bonds. For example, if you look at C here, you see the little dashed lines. Those represent hydrogen bonds. And those hydrogen bonds actually show up in these diagrams. So you can see the hydrogen bond, for example, there. Very weak. As we know, these bonds are weak, but the atomic force microscopy shows the hydrogen bonding in these systems. So these are fascinating images. All right, and here's another one where we see some weak hydrogen bonds between molecules here and here from the atomic force microscopy results. So these are just fascinating images generated by this technology. We're really beginning to see things. We really are seeing things at the molecular level and atomic level with these. Now, of course, I use the term see. And we're actually not observing these with light. These are images generated through these by electronic means. The computer programs interpret the results of the measurements and draw the image on a computer screen. But nonetheless, we can see very nicely these images of these molecular systems. And here's another one which just shows these very interesting images of these systems. In this case, hydrogen bonding again is what we're observing in these complexes. So this ends our discussion of tunneling and some fascinating results that allow us to actually image molecular systems. So in our next video, we'll be talking about systems associated with the Heisenberg uncertainty principle and begin to look at some applications to molecular structure.